Up until now in this course, we've restricted our analysis to bar elements, where all of the forces and distributed loads were applied along the length of our bars. And in the x coordinate in the coordinate system I've drawn here. We're now going to move on, and over the next few lectures, we're going to develop finite element methods to deal with beam problems, where no longer are the forces applied in the x direction, but I will have and be applying forces in the y direction. I can also apply distributed loads. And now that I'm applying forces and there will be bending in the y direction, I can also apply external moments to my bar element. Now the bar itself, of course, will have some cross-sectional area, which may be constant or may be a function of x. It'll have a Young's modulus, which may be constant or may be a function of x. And we'll have a new parameter I, which is a parameter of the material the beam is made out of, and that I stands for the principal moment of inertia, and we'll discuss that more in later videos. Because I'm applying forces and I'm applying moments along the length of my beam, that means I expect I will also get some reaction force and a reaction moment due to interaction of the wall, because the bar is not moving, the beam is not moving, all of the forces need to add up to 0, and all the moments need to add up to 0. All right, what am I interested in solving for when I do a beam problem? In bars, I was looking for the displacement of each point along the bar in the x direction. Now, when I apply external forces and moments to my beam, I expect the beam to displace not in the x direction, but I expect after I apply all of my loading that the beam will displace in my y direction. And for each point along the beam, the amount of this displacement will be different for different values of x. That is, that my displacement in the y direction is a function of x. Now, I'm also interested in knowing how much the bending is occurring at one point. One way to talk about that is to look at the angle between the unloaded bar and the angle of the loaded bar at each point along the beam. So I'm interested in an angle we will denote as phi, and phi is also a function of x because that angle will be different for each point along the beam. So to summarize, we're applying transverse forces now in the y direction. We're applying moments about the z direction. Our coordinate system is such that the xy axis passes through the centroid of our unloaded beam. And we are making approximations when we're using beam theory, just like we made approximations when we were looking at bar theory. We're assuming that there's no twisting effects about the x-axis. And we're also assuming that any axial effects can be ignored in this analysis. All right, so I think it's pretty clear what this v of x is, this displacement in the y direction. Let's talk a little bit more about what phi of x is, this angle we're talking about. It's a little hard to see on this figure, so I'm going to draw this figure again a little bit bigger, just zoomed in on this section. Okay, so what you're looking at now is a small section of my beam. Here's the unloaded beam. Here's the loaded beam. I am greatly exaggerating the amount of bending for the purposes of defining what this angle phi is. All right, if I want to find the angle phi at this point, I can approximate that by looking at some small change in my x position, dx, and my y position will change from here to here by some small amount we'll call dv. If I want to know what this angle phi is, that angle phi, the tangent of this angle phi is equal to the opposite over adjacent, that is dv dx. But if I'd like to simplify further, I can take a look at the plot for a tangent function. So if I plot a tangent function for any angle, phi or theta, remember that my tangent function looks something like that, where in the small area near the origin where theta or phi is close to 0, my value for tangent theta is almost the same as my value for theta, because that's almost a 45-degree angle straight line. So I can approximate and say that phi is approximately dv dx, and even though it's not strictly true, we're going to assume that all of our phis are so small, all of this deformation is so small that this is more or less true, and we'll just take that squiggly equal sign as an equal sign for the rest of our analysis. All right, so now I have phi as a function of x, I have v as a function of x. What am I trying to solve for, and what am I trying to do when I analyze beam problems? Obviously, I'm interested in finding this function v of x, or approximating this function v of x. I'm also interested in approximating my phi of x, which again we just denoted as dv dx. Remember, that's the angle the loaded beam makes with the unloaded beam as a function of x. Of course, we're interested in finding the reaction forces, just like we were in bar elements, but now that we're looking at beam elements, we're also going to need to find the reaction moments. Just like in bars, we were interested in finding the stress and the strain, we'll be interested in finding the stress and the strain here as well. All right, in the rest of this lecture, we will, in the next video, we will develop a differential equation for a beam that represents and models beam problems. That differential equation is known as the Euler-Bernoulli equation. In the rest of this lecture, we will develop the direct method for beam element problems. In future lectures, we will develop methods based on the principle of minimum potential energy and Glerkin's method.